Hello everyone, welcome to EEEE lecture number 43C. Today we are going to discuss about equivalent circuit of a practical transformer. So this equivalent circuit provides complete details of the current and their components, voltages, winding parameters of the primary and the secondary winding of a transformer, all represented in one common electrical circuit. It is also helping us to predetermine the behavior of the transformer under various conditions of operation. So let's draw the equivalent circuit of a practical transformer based on the topics which we have discussed so far in the two lectures on transformers. So this is a practical transformer. This is my iron core. Let me show it to you. This is my core of the transformer core. This is my primary winding. Okay. This is my secondary winding, my AC input primary voltage, my primary current I1, my magnetic flux linking the secondary and the primary winding. This is the mutually induced EMF E2. E1 is the self-induced EMF, and I2 is the secondary current or a load current, and V2 is the load voltage. So this is the practical transformer with load. You know, earlier we have studied uh, a transformer with no load, but this is a practical transformer with a load. So the practical transformer is shown over here. Now that can be represented as an equivalent circuit. So let's draw the equivalent circuit of a practical transformer. So a transformer will consist of primary winding resistance, leakage reactance X1, this is R1. And then remember last time we have discussed about no load current I naught. That is due to two current components, right? IW and I mu. Let me redraw this. Okay, so this current component is called as IW, which is the working current component or the iron loss current component, and this current component is the magnetizing current component I mu. All right, and the effect is represented as R naught, R0, and X0. All right, this we are drawing for the first time to represent the effect of no load current. Okay, now let me draw the primary winding. So this is the primary winding. Then let me draw the secondary winding now. In the secondary winding, we have R2 and X2. Secondary winding resistance and leakage reactance at the secondary winding X2. And this transformer is loaded. So we have a load connected at the output. So this is my load. Okay, let us mark the current now, or let us mark the voltages now. This is my voltage V1, AC voltage V1, or we can call it a primary voltage. The current passes through it, R1, I1, and it gets split into two parts, I0, and here we can write I2 dash. Alright, so I0 is the no load current, split it into two parts, IW and I mu. And we have seen that before, how to draw I naught. Due to the current passing through the primary winding, we have a self-induced EMF E1. Due to the self-induced EMF E1, EMF is induced in the secondary coil because of the flux linking between the primary and the secondary, and that mutually induced EMF is called as E2. Whenever we connect a load to it, a current starts flowing, which is called as a load current or the secondary current, and at the output we get the load voltage or the secondary voltage as V2. So this is how the equivalent circuit of a practical transformer looks like. Alright, at the primary side we have R1 X1. Then to represent the no load current, we have R0 X0. The current flowing through them are IW I mu. Then we have I2 dash, which is the combination of I1 and I0. And at the secondary winding we have R2 X2. current flowing is I2, and we have a load. Across the load we have a voltage Z, uh, V2, and the load impedance we can mark it as ZL. Alright, so this is the equivalent circuit of a practical transformer. Here we have representing the winding resistance by R1, R2. Leakage reactance are represented by X1, X2. This is just a representation. No load current has two current components, IW, which is in phase with voltage V1. We have discussed about this. And I mu, which is lagging behind the voltage by voltage V1 by 90, because it is due to the inductive components. An inductive component, the current lags behind the voltage. So this in this figure we have I0 is represented by pure inductor X0, taking the magnetizing component I mu, which we have seen over here, and R0 is taking the working component IW. Alright, R0 and X0 are connected in parallel across the primary circuit. So this is the first time we have represented this. So R0 represents the core loss. So therefore I square W into R naught is my core loss of the practical transformer. Just remember it. Okay. Now, if I want to draw an exact equivalent circuit of a transformer referred to the primary side, that can be obtained by transferring the entire secondary circuit to the primary side. Alright. So what we want to do is as follows. We want to transform R2 and X2 into primary side. Okay, so we'll be shifting the parameters of the secondary to the primary. Alright, so let's redraw it. How does the circuit will look like? So primary side will remain, the components will remain as it is. So let me draw it. R1, X1. Then we have I0 current flowing. It has two components, R0, X0, and this will correspond to IW, I mu. So far it is similar. Now next, whenever a secondary element is being transferred to the primary, it is divided by k square. We have seen this before, right? So this resistance is called as R2 dash divided by k square. Alright. Similarly, the reactance X2 dash will be X2 divided by k square. So any secondary element is divided by k square when transferred to primary. Alright. And we have a load voltage that is also being transferred, let's say, and the output voltage VL, V2. So V2 dash also will be V2 divided by K. So all of that is transferred to the primary side. So this is the exact equivalent circuit of the transformer referred to the primary side. So all the secondary values are referred to the primary. So now let me complete this. This current will be I2 dash, which will be same as I2 times K. This current is I1. The voltage over here is V1. The EMF induced over here is E1. The EMF induced over here, E2 dash, will be E2 by K. Alright. Then this is X2 dash, R1 R2 dash, that is there. Then ZL dash will be ZL upon K square. So if the load is having an impedance, it will be divided by K square. So this is the entire exact equivalent circuit of the transformer referred to the primary side. Alright. And this we call it figure number 3. So that's how you draw it M. Now next, in figure number 3, all the secondary resistance and the reactance are transferred to the primary by dividing them by K square. K is the transformation ratio, and all the voltages V2 and E2 in the secondary becomes V2 by K and E2 by K. Okay, this becomes V2 by K, E2 by K when referred to as primary. Okay, all the secondary current, that is I2 dash, is been transferred to the primary by multiplication of k square. So this will be multiplied by k square. This is k square. All right. So now we do another approximation. What we want to do is we want to shift this parallel branch of R0 and X0 before R1 and X1. Okay, so we'll see the obvious advantage later. We can add the resistance then, right? So while we do this, we can do this, and this is called as an approximate approximation. And due to this, the primary and the secondary impedance referred to the primary can be added conveniently. We'll see that after doing it. So now next will be to shift the parallel branch of R0 and X0 to the input side. So keeping this as a reference, you can draw this in your notebooks. Keep this as a reference. Now we just shift this parallel branch to the left hand side of R1 X1. So let's do that over here and see. So first of all, we'll shift the parallel branch. It consists of R0, X0, and then the winding resistance come R1, and then we can club together R2 dash, then we have X1, we can club it with X2 dash. R1 dash we have known it is this is R2 dash is basically R2 divided by K square. X2 dash is X2 divided by K square. Alright, and we can connect a load over here, ZL dash, which is given by ZL by K square. We are just shifting the parameters, that's it. Everything else remains the same. Here the voltage, secondary voltage will be V2 dash, which is V2 upon K. Then let me mark this currents now. This is voltage V1, current I1, I0, IW, I mu. This current flowing over here is I2 dash. Okay, this is R1, R2, X1, X2 dash. Alright, and here we have, let's say, the voltage. We can mark the voltage E1. And here we can mark the secondary voltage E2 dash, which is E2 by K. Okay, and not marked it properly. Actually, R1 and X1 should come over here, and then we can call it E1, and R2 dash and X2 dash should come over on that side, and that's what. Let me rearrange that. Okay, let me rearrange it so that it looks proper on paper. So R1 and X1 will come together. Let me take the black pen and do it. X1, and then we have R2 dash and X2 dash. Now this will be exactly proper. X2 dash, R2 dash, and now we can easily mark the induced EMFs. This is E1 and this will be E2. E2 dash will be E2 by K. Alright, so this is how we have shifted this parallel branch R0 parallel to X0 to the input side. Okay, now what it is doing is, let me just write this formula, R2 divided by K square. This is X2 dash, X2 divided by K square. Okay, what it does is as follows. Due to this, the primary and the secondary impedance and the resistance referred to the primary can be added conveniently. So that's the advantage. So how can it be added conveniently? We can add R1 plus R2 dash, which we can call it as RO1, and we can add X1 plus X2 dash, which we can call it as XO1. All right. So this RO1 and XO1. Now this diagram, I mean, this is the approximate equivalent circuit. Now this is the approximate equivalent circuit of the transformer as referred to the primary side. Now let us draw that approximate equivalent circuit with this added up reactance and resistance. So let me draw one final circuit with approximated parameters. So this is just, we can show just a cumulative resistance and a reactance. Okay, and the transformer is loaded with ZL dash. Here the voltage is V2 dash. This is XO1, RO1. This is I0. This is my voltage V1, current I1. And here it is I2 dash. So now I want to represent them. Let me add over here IW, I mu. This value of the resistance is R0 and X0. So this is my approximate equivalent circuit of the transformer as referred to the secondary side. Okay. So this is the equivalent circuit of the transformer. Actually, we have drawn it above only. Here only we have drawn it. So this is figure number, let's say A. So as shown below, as shown in figure A, we can write. We have drawn it up only. It's fine. Drawn as figure A above. Okay, so you have already drawn it. That's nice. This is the approximate equivalent circuit of the transformer as referred to the uh, primary side. Now let me write few things from here. Now what is RO1? RO1 is basically R1 plus R2 dash. Okay, so let me add it over here. RO1 is, from that diagram, R1 plus R2 dash, and R2 dash is what? R1 plus R2 upon K square. Similarly, what will be XO1? XO1 will be X1 plus X2 dash. XO1 will be X1 plus X2 dash, which will be X1 plus X2 upon K square. And similarly, what will be ZO1? ZO1 will be RO1 plus J times XO1. And if I want to write the magnitude, ZO1 will be square root of R0 square plus RO1 square plus XO1 square, and that will be norms. So this is what the parameter means. The main parameters of this approximated circuit are, of the approximated equivalent circuit of the transformer are RO1, equivalent resistance of the transformer as referred to the primary side. XO1 is the equivalent reactance of the transformer as referred to the primary side. RO is the equivalent core loss resistance, and X0 is the magnetizing reactance. All right. So yeah, that's it from this topic. No need to add point number 13. We have already included all the stuff above. All right, clear. So we started with a exact equivalent circuit of the practical transformer, and we have come to this approximate circuit of equivalent circuit of a transformer with the parameters written described over here. All right. Okay. If they ask you a practical circuit, equivalent circuit of a transformer, you can follow the steps. Now let's go to the next one. And write over here topic below. Okay, let's move on. Now we have talked about before transformer on no load. Now we'll talk about transformer on load. So when transformer is on no load, that is when the secondary winding is open circuit, or I2 is 0, the primary winding draws a very small current I0, and phi is the main flux in the core. So this is the situation over here. V2 is open, that means the secondary is open, and we have not connected any load. So the current I2 will be, secondary current will be 0. Alright. And I1, the primary current will be given by I0 plus I2 bar, I2 dash. Okay, we have seen this before. So when the secondary winding is loaded, the secondary current I2 is set up. The secondary current in the secondary of the transformer, secondary winding of the transformer is set up. The magnitude and the phase of I2 with respect to V2 depends upon the nature of the load. Okay, whether it's inductive, resistive, or capacitive. So when the transformer is connected to the load, the primary winding has two current component in it. One is I0 and one is I2 dash. We have seen in I0 also we have two. One is IW and the other is I mu. Okay. So collectively your primary current will be given by, this is the primary current, total primary current will be given by the phasor sum of I0 and I2 dash. Okay. So considering this in picture, let's draw the phasor diagram of transformer, let's say without considering winding and leakage reactance. Okay, so what does that mean? We'll draw the let's draw the equivalent circuit of the transformer without winding resistance and leakage reactance. So this is the circuit, right? We have I1 is the primary current, total primary current, which is given by I0. This is the no load current plus I2 dash. All right, we have seen this, how this comes. On the primary side, E1 is equal to V1, but are anti-phase with each other. Okay, so we can write over here properly, E1 and V1 are equal in magnitude but opposite in phase. So E1 is equal to minus of V1. Okay, that means they are anti-phase with each other. On the secondary side, E2 and V2 are in phase. Okay, this is considering that there are no winding resistance and leakage reactance, so E2 will be equal to V2 and V1 will be equal to minus of E1. So let us draw the phasor diagram for the following loads: resistive load, inductive load and capacitive load. Alright, let's draw it. So let's say the load is resistive first. That means we have a unity power factor. Also we are considering that the transformer ratio K, which is given by E2 upon E1, is 1. That means E2 is equal to E1. And we have seen before, while discussing the EMF equation of the transformer, that the EMF induced E1 and E2 are lagging behind the reference phasor phi by 90 degree. That means where will E1 will come? Let me draw it. Where will E1 and E2 will come? E1 and E2 will lag behind the reference phasor by 90 degree. So if this is E1, E2 also will be same. So E1 will be equal to E2. Okay, they are one and the same. So let me add over here. E1 will be equal to E2. All right, but we know that E1 and V1 are out of phase. Okay, E1 is basically minus of V1. So here minus of V1 can be drawn like this. So this is my V1. All right, clear? Okay. Now we have to draw. Let me show you the diagram. Current I2 is in phase. If the load is resistive, I2 and V2 will be in phase with each other. So we can write as we have resistive load I2 is in phase with E2. Okay, so that means, let me use a green color. That means I2 also will be here only. That means if the phase angle between them is phi 2, the phase angle is 0. Is this clear? All right. Now, next we have to take into consideration this vector sum. I1 is I0 plus I2 dash. So let me add over here one. Let me write this vector equation. I1 is I2 dash plus I0 bar. Now I2 dash is opposite of I2, right? So if this is I2, I2 dash will be above. So this will be I2 dash because they are in antiphase with each other, right? Now what about I0? I0 bar. So let's say I0 bar is having it's leading the phi, reference phase phi, like this. This is I0 bar. So how will I draw I1? I1 is the vector sum of I2 bar and I0 bar, right? So it will come something somewhere like this. Using the law of parallelogram, it will be something like this. Okay, so this is your I1 bar. Okay, this is the primary current. Now, what is the phase angle between the primary voltage and the primary current? Phi 1. So this is my phi 1. And what is the phase angle phi 2? Phi 2 is between V2 and I2. So let me add over here. Phi 1 is the phase angle between V1 bar. I mean everything is bar over here basically. V1 bar and I1 bar. Alright. And phi 2 is the phase angle between V2 and I2. Of course, that we have to take care. This phase angle is 0 over here. Now this is the difference. For any other load other than the resistive load, this phi 2 won't be 0. So let's see now further. Let's draw it for load is inductive. So load is inductive, the procedure is similar. Only thing is when the load is inductive, your current I2 lags behind V2 by an angle phi 2 which is lesser than 90 degree. And as the load is inductive, this is what we have to take care. Rest everything is same. So let me draw. We have a reference phasor. We first draw E1 and E2. E1 and E2 are same. So this is E1 equal to E2. E1 that is equal to V2 because E2 and V2 are same. Sorry, I have not drawn it over here. Yeah, even this is also equal to V2. So why? Because E2 and V2 are same. Here you see E2 is equal to V2. Okay, so we have drawn this, and now how do we draw I2? Where will should we draw I2? Yes, correct. I2 lags behind V2, so it will come somewhere around here, lesser than 90, let's say. So this is my I2, and this phase angle is phi 2. Let me expand it and show it to you. Yeah, this phase angle is phi 2. Now the above one is simpler. Now we draw the you know I2. This is I2, so this will be I2 dash. Now how we will draw? This is E1. So V1 will be in antiphase with E1, right? So let me draw it over here. This is V1. Okay. Now where will I draw I0? I0 bar. So I0 bar is lagging. It's leading the reference phasor. So this is your, let's say, let me add a different color. This is I0 bar. Now we know that I1 bar is I0 plus I2 bar is the vector sum of it. So by the law of parallelogram, where it will go in the middle of these two, like this. and by law of parallelogram we get the vector. So this vector is my I1 bar, and I1 bar is the primary current. So where will be the phase angle now? Phase angle phi 1 will be between I1 bar and V1 bar. So this is my phase angle phi 1. So what was the difference between previous diagram and this diagram? This I2 and V2 were in phase, and here we have a phase difference because I2 is lagging behind the voltage V2 by an angle of 90 degree, less than 90 degree. Okay, so this is the phasor diagram when the load is inductive. Now what happens when the load is capacitive? Yeah, when the load is capacitive, same story will repeat. Let me start by drawing it. We have E2 equal to E1, which is equal to V2, and here we have V1. Okay, this is clear, right? Now we say the load is capacitive. So in a capacitive load, what happens? The current lags. No, current leads the voltage, not lags. Current leads the load voltage V2 by an angle phi 2 less than 90 degree. Okay, so leading means it will come over here. Let's say let's draw it again. Okay, and let me call it as I2 bar. This is E1 bar. Yeah, this is I2 bar, right? So I2 bar. So I2 dash will be exactly opposite. This will be I2 dash. All right. So this phase angle between I2 and V2 is called as phi 2. You have written it, right? Now where is I1? I0? I0 we have written the equation before. I1 bar is total primary current is I0 bar plus no load current plus I2 dash. Now I2 dash is drawn. Here we have to draw I0. This is, let's say, I0. So where will be your this thing I1? Let me draw I0 properly. Okay. So your resultant V1, let me rewrite this over here. This is V1 bar. Okay. So where will I1 is the vector sum of I0 and I2 bar. All right. And the vector sum will come somewhere around here. Okay. Let me redraw it over here. Okay. Exactly, it will be a parallelogram. Now this is not exactly a parallelogram. Let me draw it properly. Yeah. So this is your I1 bar. So I1 bar is my primary current, V1 is my primary voltage. So phase difference between them is phi 1. So that's how you draw the phasor diagram when the load is capacitive for a leading power factor. All right, clear? Okay. But in the exam, if they ask you the phasor diagram of a practical transformer, we have to consider the winding resistance R1 and R2 and the reactance X1 and X2. We cannot draw the previous diagrams. That is simplified version. Okay. So to draw the actual one, we have to consider the following vector equations. In the primary side, V1 bar is given by I1 bar into R1 bar, I1 into X1 bar, and then E1 is in the phase difference with V1, so minus of E1 bar. All right, simple. Okay. Next is E2. E2 bar will be I2 R2, I2 X2 plus V2. All right. And then I1 bar, which is the total primary current, will be I0 plus I2 dash. So phasor diagram can be drawn with the help of these three equations. The phasor diagram can be drawn with the help of these three equations. Now listen very, very carefully. Start opening your books and draw it along with me. So first of all, there are following assumptions that when the load is resistive, we have a unity power factor. Assuming the transformer ratio as 1, E1 will be equal to E2. Okay, E1 will be equal to E2, and phi is my reference phasor. And phi is my reference phasor. Let me write those three equations. Those will come in handy. So those are V1 bar is equal to I1 R1 plus I1 X1 minus E1 bar. Then E2 bar is I2 R2 plus I2 X2 plus V2 bar. And what is I1? I1 is I0 plus I2 dash. All right, let's start now. So when the load is resistive, what is the phase difference? Phi 1. Your phase difference phi 2, the phase angle phi 2 will be 0. Why? Because the phase difference between, okay, the phase difference between I2 and V2 is 0. When the load is resistive, right? When the load is resistive, the phase difference between V2 and I2 will be 0. Okay, so this we should keep in mind. Now, first is a reference phasor, right? Phi. So we know already that E1 and E2 are same because we have written over here, right? E2 K is 1, so E1 is equal to E2. Phi is the reference phasor, and flux phi leads the E1 and E2 by 90 degree. We have seen this. E1 and E2 induced EMF lags behind the reference phasor by 90 degrees. So let me start by drawing it. So this is my E1 equal to E2. They are in phase with each other. All right. Now next next comes where will your current I2, okay, all right, let me maximize this. We have drawn E1 and E2 so far, and they are lagging behind a reference phasor phi by 90 degree. So this is 90 degree. Okay, I hope I'm giving you all time to draw so that you can draw along with me. Next, we have drawn earlier also the how we have drawn this I1, I0, and I2 dash. All right. The same way we have to draw this also. So I0, I'll draw it like this. I0 bar, and then I2. Where will I2 come? Yeah. Okay. So first of all, we should remember. Let's before going to I0 bar and everything else, let's focus on this one. This equation. E2 bar is I2 R2 plus I2 X2 plus V2. All right. Now the phase difference between V2 and E2. How will know? How will know? I mean, there is no phase difference between V2 and I2. Okay. So V2 and I2 phase difference is not there. And here, if I have a component like this, just a second. All right. So first we have to draw V2, right? So V2 can be drawn like this. Let me take the color. So V2 have to be drawn like this. Okay. Let's say this is V2. Where will I2 come? I2 will come in the same phase. So this is V2 bar, I2 bar. All right. And where will I2 we have I2 R2 also. So I2 and R2 also will be in the same direction. This is V2 bar. This is I2, and in the same direction only you will get I2 into R2. The voltage drop also will be in the same direction. Now, where will this come now? I2 X2. Now, if it is a reactive, now X2 I2 X2 will be 90 degree out of phase, right? With I2 R2, right? Why? Because this will be a reactance, and this reactance will lag behind that. All right. So we have E2 is I2 R2 plus I2 X2 plus V2. Okay. So this is V2. I2 X2 is this. All right. Okay, fine. So let's restart our approach. Okay. So for drawing this phasor diagram, first of all, we have to start with first draw V2. Okay. So let's say V2 is over here. Let's say this is V2. All right. And then draw I2. So V2 and I2 are in the same direction. This is V2. This is I2 because they have no phase difference, right? We have written over here phase difference between I2 and V2 is 0. So basically we can say phi 2 is 0. Okay, phase difference between them is 0. Phase angle between them is 0. And that will depend upon the type of load. It is resistive load, so phase angle between them is 0. Alright. Now, as per this equation, we have to add I2R2. So I2R2 will be another drop. So this will be extended further, and this we can call it as I2R2. Alright. And we have V2 also. Now now what we had is to add V2, we have to add the resistive drop I2R2 parallel to I2. So that's what we have extended, and inductive drop I2X2. So I2X2 will be leading I2R2 by 90 degree. Okay, this will be leading by 90 degrees. So you have to draw this line. This will be 90 degree. And why this will be 90 degree, I will be telling you in short. This is I2 X2 bar. Okay, so this will be I2 X2 drop, resistive drop I2 R2 will be leading the inductive drop I2 X2 by 90 degrees. So this will be 90 degree, right? And all of their vector sum will be equal to E2. So I2 R2 plus I2 X2 plus V2 will be leading to E2. So now we'll draw E2. So this much is E2. Alright. This much is E2. Now it is clear. Now, since the transformer ratio K is 1, E2 is equal to E1. Clear? Is it fine? E1 and minus E1, I mean V1. So E1 is over here. Minus E1, how will you draw? Like this. This is minus E1. So far so good. This is E1, so this is minus E1. Alright. They are same, they are equal. So they are equal, but they are opposite. Right? Opposite in phase. Now, for drawing I1, first we have to draw I0. So this is I2 bar, right? Now I have to draw I2 dash I2 one bar, like this in parallel opposite, right? So this will be I2 dash bar, I2 dash bar. Because this is I2, so this will be I2 dash bar. And we have to draw I0. So I0 will be somewhere around here, let's say I0 bar. So I1 will be the vector sum of I0 bar plus I2 bar. So let's draw this vector sum first. So we are going through this equation now. I1 bar will be the vector sum of I0 and I2 bar, and that will be treated as per law of parallelogram. We can find out as per the law of parallelogram. So this vector is I1 bar, which is the primary current. Okay. So far any confusions? All right. Hope so not. Yeah, I sincerely hope so not. So we have added I0 to I2 bar using the parallelogram law of vector addition, such that I1 bar is I0 bar plus I2 bar. Now further, concentrate on this equation now. V1 bar is I1 R1 I1 X1 minus E1, right? So it's an addition of all these three things. Now 2 minus E1, we have to add a resistive drop. We have to add a resistive drop, and this resistive drop is I1 R1. Now this I1 R1 should be parallel, so this we have to draw in parallel to I2 R2. So this should be parallel to I1 actually. So this is I1, right? So it should be parallel to I1. Let me show it to you. This is E minus E1 bar. I1 R1 will be parallel to this. Let me draw black color. Okay, this is I1 R1, and um, inductive drop I1 X1 will be leading I1 R1 by 90 degree. So we have to draw another one now, 90 degree like this. Okay, let me draw 90 degree properly. Uh, it's okay. I have to properly draw 90 degree. The bending doesn't go properly over here. Okay, I have to, let me draw it properly. Okay, yeah, let's consider this now final. This is this, what is this vector component? I1 X1, and this is drawn 90 degree like this. So if you draw it in your paper, it will be proper for you. So this is I1 X1, this drop is I1 R1, and we have E1 bar over here. So this all three together will be V1, right? So this will be V1. This will be, all will be equal to V1. So V1 will be from here. Understood? So this drop is your V1. Understood how we have drawn? E1 bar plus I1 R1 plus I1 X1 is equal to V1. Alright? Okay, understood? Now let us draw the various phase angles. So what is the phase angle between V1 and I1? Phi 1. So phase angle phi 1 is between V1 bar and I1 bar. So let us draw that. This is the phase angle. Okay. So this phase angle is phi 1. This is phi 2. We have drawn that phi 2. Alright. Any doubts here? And we will also have phi 0. Phi 0 is the phase angle between I0 bar and V1. So we can draw that also over here. I don't want to complicate it further. So that's how you start. Alright. So this is how you draw the phasor diagram for the load, resistive load. We have to be very careful. Initially we have started and made some mistakes, but it's fine. It will come by practice. That is how the diagram will look like. Is it fine? Okay. Now let's draw quickly for when the load is inductive. When the load is inductive, we have to draw the phasor diagram of a practical transformer for the inductive load. So you have to follow the same procedure, okay, as we have followed the resistive load. Only one difference is there. And what is the difference? The difference is that for an inductive load, the current lags behind the voltage. Okay, what I'm talking about is this. For as the load is inductive, so due to inductive nature of the load, your current I2 lags behind the voltage V2 by an angle phi 2 less than 90 degree. So only this difference is there. Rest everything, entire procedure remains the same. Alright. So let us start now. So this is my reference phasor. First of all, I have to draw the reference phasor. So let me first I'll draw V2. So let's say this is my V2. Alright. Where will my I2 come? I2 will be lagging behind. So it will be lagging behind somewhere around here, let's say. So this is my I2, let's say. I2 bar, we can say. This is my V2. This is my V2. Okay. Now where will I2 R2 come? I2 R2, I have to draw a line in parallel to this. I mean, it should be parallel to I2. Okay. So this is I2 R2. Alright. This I have drawn in parallel to I2. Okay, I2 R2. And 90 degree from there, I have to draw what? I have to draw 90 degree from here. Okay, so this is 90 degree. I have drawn over here what? I2 X2. As we have done last time, right? I2 resistive drop is I2 R2, right? So this I2 is parallel to this, and this is V2. So 90 degree here we have drawn I2 X2, and that is equal to E2. So E2 I will be drawing it over here now. Let me take a different color, blue one. So this becomes my E2, and E2 is equal to E1 because the transformation ratio is 1, K is 1. Okay. Now E2 opposite, I have to draw minus E1. Now this is over. Next is very simple. I have to draw minus of E1 bar. This is E1, E2 because we require this over here, right? Now we concentrate on this part. Okay. First of all, let's clear up I2. So I2 opposite will be what? This is I2. So parallel to it, we'll draw I2 bar. All right. So I2 bar, we know that I2 bar plus I0 bar will be I1. So let's draw I1. So this is I0 bar, and I1 bar will be the vector parallelogram according to the parallelogram of vector addition. It will be somewhere like this. I mean, I have not drawn it properly, but this will come very much proper once you draw to scale. Okay, so let me add it like this. Yeah. So this is your I1 bar, this one. Okay, this is your I1 bar. Actually, I have not drawn I1 properly. I1 has to be exactly in opposite. Okay, fine. I1 bar is drawn. Now this is over. This is done. Now we come back to the first one. We have drawn E1. So to E1 we have to add I1 R1. So where is I1? So I1 is here. We have to draw something in parallel. It's in parallel now. Parallel to this. So this is I1 R1. Okay. Now in order to draw I1 X1, it has to be 90 degree from here. So 90 degree from here, somewhere around here it will be. This is 90 degree, right? This is 90 degree, so this will be I1 X1 bar. Alright. And then the addition of all three, I1 R1, I1 X1 and E1 will give us V1. So this plus this will giving us the resultant vector V1. So the resultant vector V1 will be from here. Okay, let me draw properly. Straight line is little difficult to draw with this. Yeah, this is your V1. I hope you got it. Now this is similar to what we have done before. Alright. And this becomes your phasor diagram when the load is inductive. Let me minimize it and show it to you. Yeah, this is the complete picture. Only difference was I2 and V2 were having a phase difference of phi 2, which is I2 was lagging behind the voltage V2. Let me draw the various voltages. I mean the phase angles. So there is a phase angle between I2 and phi 2. So this is called as phi 2. Okay. Then there is a phase angle between I1 and V1. So this is I1, this is V1. So this phase angle is phi 1. And there is a phase angle phi 1 is between V1 bar and I1 bar. Phi 2 is between V2 bar and I2 bar. And there is one more phi 0. It is between I0 and V1. So we can draw it, but it will complicate the things, but that is what we have written. Okay, so if you show this much information, that's enough. That is enough. All right. So let's quickly move on to the load is capacitive phasor diagram, and it is the last one for this lecture. Let's draw it quickly now, this one. So since the load is capacitive, a capacitive load, so in a capacitive load, your current I2 leads V2 by a phase angle phi 2 less than 90 degree. Okay, so let's start drawing the phasor diagram now. So first of all, we'll start with V2. So let's say V2 is over here. This is V2. So where will be I2? This is I2. Where will be this is V2. So where will be I2 now? Leading. So let's say this is I2 bar, of course. And the phase difference between them is phi 2. That we'll draw it later. Okay. All right. Now to this V2 we have to add I2 R2. So we'll take this, draw I2 in parallel. Okay, I have to draw it in parallel. It's not coming properly, but it will eventually come. Yeah, this is I2 R2. Okay, I2 R2 is the voltage drop, I2 R2, and 90 degree to this voltage drop will come I2 X2. I2 X2 will be 90 degree. I2 R2 will be leading I2 X2 by 90 degrees. So let me see if I can draw a straight line properly. Yeah, this is 90 degree. And then the addition of all means I2 R2, V2 and I2 X2. This is I2 bar x2 bar is nothing but your E2. So this is your E2. This much is your E2. E2 is equal to E1 because transformation ratio is 1. Alright, so this much is clear. Rest above 1 is very simple. Now we have drawn I2. So I2 dash, this will be I2 dash bar. Right, now I0 I can draw it very simply. I0 will be somewhere around here, let's say. So what will be I1 primary current is the vector sum of these two. So primary current I1 will be vector sum of I0 plus I2 bar. Okay, just a second. Okay, so this is your I1 bar. All right, and now we have to draw minus E1. So we have to draw this much length and then opposite. Let me take this out. Okay, so if this is E1, this will be minus E1. Let me add over here minus E1. Okay, now we'll go over here. To this E1, I have to add I1 R1. So this is I1. I have to draw in parallel. Let's say this is I1 R1. Now to this I1 R1, I have to take 90-degree line and add I1 X1. So let's say this is 90 degree and this is I1 X1 bar. Alright. And now finally E2, V1 is I1 R1, I1 R1, I2 X2 plus E1 bar. Now let me write this E1 bar on that side. This is minus E1 bar, and V1 will be this, the resultant vector from here to 0. Hopefully it goes. Yeah, it goes. So this is your V1 bar. Alright. I hope it is clear now. We have done it 3 times. Now let us write the various phasors, phase angles. Phi 2 is between V2 and I2. Phi 1 is between V1 and I1. So let us mark that phasors over here. So this is V2 and I2. This phase angle is Phi 2. And here it is V1 and here it is V1 and I1. So this phase angle is Phi 1. Okay, and this completes the phasor diagram of a transformer, practical transformer. If it comes in the exam, it will definitely come for some marks, and you have to draw it systematically like the way I have shown over here. Okay, all right. I hope it is clear. You can pause and rewind the video and check how I have drawn it step by step. Okay, so that's it for this lecture. Next time some more topics are to be covered, that is rating of a transformer, then efficiency of a transformer, derivation for maximum efficiency, and voltage regulation. So let's quickly